Here we are, 7 billion minds on a small blue world, staring into the cosmic dark and wondering why the universe seems so remarkably, stubbornly quiet. Tonight, we'll explore one of the most profound puzzles facing our species, a question that has haunted physicists, philosophers, and dreamers for generations. The universe should be teeming with life, yet we find ourselves apparently alone in an ocean of silent stars. This is a journey into the great cosmic mystery of our time. So settle back, let your shoulders relax, and allow yourself to drift into contemplation of questions that span billions of years and countless worlds. There's no need to grasp every detail or remember every theory we'll encounter. Simply let the vast scales of space and time wash over you and forget about the ticking of clocks entirely. The silence is almost too perfect to be real. In the summer of 1950, a brilliant physicist named Enrico Fermi sat down to lunch with colleagues at Los Alamos National Laboratory. The conversation had turned to recent UFO sightings and the possibility of extraterrestrial visitors when Fermi suddenly paused mid-bite and asked a question that would echo through decades of scientific inquiry: where is everybody? The question seems almost laughably simple at first glance, but Fermi had done the mathematics in his head during those few moments of silence. He understood something that would later crystallize into one of the most troubling paradoxes in modern science. If the universe operates according to the laws we observe, if stars form planets and planets can harbor life, if intelligence can emerge and develop technology, then our galaxy should be absolutely bustling with alien civilizations. The night sky should be alive with their signals, their megastructures, their obvious presence. Instead, we peer into the darkness and hear nothing but the whisper of cosmic background radiation. The numbers behind Fermi's casual lunchtime observation are staggering in their implications. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Recent observations by the Kepler Space Telescope and other instruments suggest that rocky planets orbiting within their star's habitable zone, that precious distance where liquid water can exist, are remarkably common. Conservative estimates suggest there might be 20 billion potentially habitable worlds in our galaxy alone. Even if we apply extremely pessimistic probabilities to the emergence of life, the development of intelligence, and the rise of technological civilizations, the numbers remain overwhelming. If only 1 in a million habitable planets develops intelligent life, and only 1 in a million of those develops interstellar technology, we should still expect thousands of advanced civilizations in our galaxy right now. Yet, when we turn our most sensitive radio telescopes toward the stars, when we scan the electromagnetic spectrum for any hint of artificial signals, when we search for the infrared signatures of massive engineering projects or the telltale signs of industrial activity on distant worlds, we find nothing that couldn't be explained by natural phenomena. The universe maintains its cosmic poker face, revealing none of its secrets about the prevalence of mind. This profound absence has a name now, the Fermi Paradox, and it has inspired decades of increasingly creative and sometimes disturbing attempts at resolution. Each proposed solution opens new questions about the nature of intelligence, the development of technology, and our own future as a species. Some answers are reassuring, suggesting we're simply looking in the wrong places or at the wrong times. Others are deeply unsettling, implying that something prevents civilizations from reaching the stars, or worse, that reaching the stars brings its own terrible consequences. The search for extraterrestrial intelligence, known to most by its acronym SETI, began in earnest in 1960 when astronomer Frank Drake pointed a radio telescope at 2 nearby sun-like stars and listened for signals that couldn't be natural. His Project Ozma detected nothing but noise, but it established a methodology that has guided the search ever since. Listen for patterns, look for repetition, search for signals that show unmistakable signs of intelligent origin. Drake's early work led him to formulate what became known as the Drake equation, an attempt to estimate the number of communicating extraterrestrial civilizations in our galaxy. The equation itself is elegantly simple, multiplying together factors like the rate of star formation, the fraction of stars with planets, the fraction of planets that develop life, and so on. But beneath its mathematical simplicity lies a web of profound uncertainties. We now know that planet formation is commonplace, that organic molecules exist throughout the universe, that life appeared on Earth relatively quickly after the planet became habitable. These discoveries have made many of the Drake equation's early factors more optimistic than Drake himself dared hope. Yet the later factors, the likelihood that life develops intelligence, that intelligence develops technology, that technological civilizations survive long enough to communicate across interstellar distances, remain complete mysteries. The evolution of intelligence on Earth offers both hope and caution. Complex nervous systems evolved multiple times independently, suggesting that the capacity for sophisticated information processing might be a natural outcome of biological complexity. Octopuses, dolphins, elephants, and various species of birds have all developed forms of intelligence that would have seemed impossible to earlier generations of scientists. Intelligence appears to be one of evolution's favorite solutions to the challenges of survival, but technological intelligence, the kind that builds radio telescopes and space missions, emerged only once on Earth in a single species after 4 billion years of biological experimentation. Homo sapiens developed agriculture, writing, science, and spaceflight in what amounts to an eye blink of geological time. But we did so only after countless other intelligent species had come and gone without leaving any lasting technological legacy. The question of whether intelligence naturally leads to technology becomes even more complex when we consider that our own technological development has been shaped by incredibly specific historical circumstances: the availability of easily extractable fossil fuels, the presence of metals near the Earth's surface, the development of particular cultural and economic systems. Countless factors had to align to create the conditions for our rapid technological advancement. An intelligent species that evolved on a water world where fire was impossible and metals remained locked beneath kilometers of ocean might never develop metallurgy or chemistry as we know them. A species that achieved ecological balance early in its development might never experience the resource pressures that drove human innovation. Intelligence and technology, it seems, are not necessarily synonymous. Even if we assume that technological intelligence is common, the challenges of interstellar communication introduce another layer of complexity to the search. Radio waves, traveling at the speed of light, take 4 years to reach the nearest star system and tens of thousands of years to cross the galaxy. Any conversation with a distant civilization would unfold over geological timescales, making real communication effectively impossible across vast distances. This temporal challenge becomes even more daunting when we consider the lifespan of technological civilizations. Humanity has been capable of radio communication for less than 150 years, a microscopic fraction of the time that life has existed on Earth. If our civilization's radio-capable period represents a typical span for technological species, then the chances of 2 civilizations being simultaneously active and within communication range become vanishingly small. The problem resembles trying to coordinate a meeting with a friend in a vast city, where each person is only present for a few seconds out of every 1,000 years, and neither knows when the other might appear. The city might be full of people, but you'd never encounter each other. SETI researchers have expanded their search strategies far beyond Drake's original radio surveys. Modern projects scan millions of star systems simultaneously, looking for brief pulses that might indicate laser communication systems. Others search for the infrared signatures of Dyson spheres, hypothetical megastructures that advanced civilizations might build to harness the energy of their stars. Still others look for subtle signs of industrial pollution in the atmospheres of distant planets, or for the geometric patterns that might indicate large-scale engineering projects. The Breakthrough Listen initiative, funded by technology entrepreneur Yuri Milner, represents the most comprehensive SETI project ever undertaken. Using some of the world's most sensitive radio telescopes, Breakthrough Listen is surveying 1 million nearby stars across a wide range of frequencies, accumulating data at a rate that would have been impossible just decades ago. The project has detected thousands of interesting signals, but so far, all have proven to have natural or human-made origins. The lack of obvious signals has led some researchers to question their basic assumptions about how advanced civilizations would communicate. Perhaps radio technology represents only a brief phase in a civilization's development, quickly superseded by more efficient communication methods that we haven't yet imagined. Perhaps advanced civilizations use tightly focused beams or exotic physics that make their signals nearly undetectable to primitive observers like ourselves, or perhaps they're intentionally hiding. The zoo hypothesis suggests that advanced extraterrestrial civilizations are aware of us but deliberately avoiding contact, much like wildlife researchers might observe animals without interfering with their natural behavior. This idea, while untestable by definition, offers an explanation for the apparent absence of alien contact while still allowing for a universe teeming with intelligent life. The notion that we might be cosmic zoo animals raises uncomfortable questions about our significance in the universe. Are we a protected species, carefully observed but not contacted to preserve our natural development? Are we simply too primitive to merit attention from beings whose technology and understanding dwarf our own? The hypothesis implies a level of galactic coordination and restraint that seems almost too sophisticated to believe, yet it remains one of the few explanations that allows for both widespread intelligence and continued cosmic silence. A darker interpretation of the Fermi paradox centers on the concept of the Great Filter, some evolutionary or developmental hurdle so difficult that most potential civilizations fail to overcome it. The filter might occur early in the development of life, explaining why we haven't found even simple organisms elsewhere in our solar system. Or it might occur later, somewhere between the emergence of intelligence and the achievement of interstellar colonization. If the Great Filter lies behind us, if the emergence of life or intelligence or technological civilization is extraordinarily rare, then we might indeed be alone, or nearly alone, in our galaxy. This possibility, while lonely, offers some comfort. We've already passed the most difficult test and need only continue our development to become one of the few successful spacefaring civilizations. But if the Great Filter lies ahead of us, the implications are deeply troubling. Something prevents civilizations from reaching the stars, and we have yet to encounter it. Perhaps advanced technology inevitably destroys its creators through warfare, environmental destruction, or unforeseen consequences of powerful discoveries. Perhaps the development of artificial intelligence leads to scenarios we can't yet imagine. Perhaps there are physical limits to expansion that we haven't recognized, or cosmic hazards that await any species bold enough to venture into deep space. The possibility that civilizations routinely destroy themselves shortly after developing advanced technology would explain the cosmic silence while offering a chilling preview of our own potential future. Nuclear weapons, climate change, artificial intelligence, biotechnology, we're developing capabilities that could end our civilization long before we master interstellar travel. Some researchers have proposed that the filter might be more subtle, not catastrophic destruction, but a kind of evolutionary trap. Perhaps virtual reality becomes so compelling that advanced civilizations lose interest in exploring physical space, choosing instead to live in increasingly sophisticated artificial worlds. Perhaps the manipulation of matter at the quantum level makes external expansion unnecessary, allowing civilizations to create unlimited resources and experiences within very small physical spaces. The idea that intelligence might naturally turn inward rather than outward challenges our assumptions about the goals and motivations of advanced beings. We imagine that curiosity and the drive to explore are fundamental aspects of intelligence, but these might be peculiar quirks of human psychology rather than universal traits. Recent developments in our understanding of exoplanets have added new dimensions to the search for life. The discovery that many planets orbit very close to small, long-lived red dwarf stars has expanded our conception of where life might arise. These tidally locked worlds, with permanent day and night sides, might harbor life in the twilight zones between extreme heat and extreme cold, but they might also be bombarded by dangerous radiation from their host stars, making the development of complex life extremely difficult. The concept of planetary habitability has grown far more nuanced as we've discovered the incredible diversity of worlds that exist beyond our solar system. Some planets have atmospheres hundreds of times thicker than Earth's. Others have no atmospheres at all. Some orbit their stars in a matter of days, while others take hundreds of years to complete a single orbit. The range of conditions under which life might exist appears to be far broader than we initially imagined, but this diversity also highlights how unusual Earth's specific combination of characteristics might be. The rare Earth hypothesis argues that while simple life might be common throughout the universe, complex life requiring the precise conditions found on Earth is extraordinarily rare. Our planet benefits from a massive moon that stabilizes its axial tilt, a magnetic field that protects us from harmful radiation, a position in the galaxy that avoids the dangerous radiation of the galactic center, and countless other factors that might be necessary for the development of intelligence. If complex life requires such a precise combination of circumstances, then most of the potentially habitable planets we've detected might host nothing more than simple microbes. Intelligence might be so rare that only a handful of planets in the entire galaxy have ever produced it. This possibility carries its own strange comfort. If intelligence is truly rare, then every conscious being represents an almost impossible victory against cosmic odds. The emergence of human consciousness, with its capacity for science, art, and moral reasoning, becomes not an expected outcome of natural processes, but a miraculous accident that deserves profound protection and celebration. The search for alien life has also expanded to include looking for signs of past civilizations rather than currently active ones. The concept of archaeological SETI involves searching for the remnants of alien technology, ancient spacecraft, abandoned colonies, or industrial artifacts left behind by civilizations that may have existed millions or billions of years ago. Within our own solar system, researchers have proposed looking for signs of previous visitors in the geological record, in the composition of asteroids, or in the form of artifacts left on airless worlds where they might survive for geological ages. The moon, with its lack of atmosphere and geological activity, could potentially preserve evidence of alien visits for millions of years. The idea that aliens might have visited Earth in the distant past has been popularized in science fiction and pseudoscientific theories, but serious researchers approach the question with appropriate skepticism and rigorous methodology. Extraordinary claims require extraordinary evidence, and no such evidence has yet been found. But the possibility remains intriguing. If intelligent life is common, some of it might have developed spaceflight long before humans existed. Our understanding of the conditions necessary for life continues to evolve as we discover organisms thriving in what were once considered impossible environments. Deep-sea hydrothermal vents, highly acidic hot springs, the radioactive interiors of nuclear reactors. Life has colonized every available niche on Earth, often using energy sources and chemical processes that seemed incompatible with biological systems. These extremophiles have expanded our conception of where life might exist beyond Earth. Jupiter's moon Europa, with its subsurface ocean warmed by gravitational tides, might harbor ecosystems based on chemical energy rather than sunlight. Saturn's moon Enceladus jets water vapor into space from an underground sea that might have persisted for millions of years. Even Mars, now a frozen desert, shows evidence of ancient rivers and lakes that might once have supported life. The possibility that life exists elsewhere in our own solar system has profound implications for the Fermi paradox. If life arose independently on multiple worlds within a single planetary system, it would suggest that the emergence of life is relatively easy given the right conditions. But if we find no trace of life anywhere else in our solar system, despite the apparent prevalence of potentially habitable environments, it might indicate that life is far rarer than we've assumed. The development of increasingly powerful telescopes and analytical techniques has allowed astronomers to begin studying the atmospheres of distant planets. The James Webb Space Telescope can detect the chemical signatures of water vapor, oxygen, and other potentially biological gases in the atmospheres of nearby exoplanets. Within the next few decades, we might be able to determine whether any of these worlds show signs of active biological processes, but interpreting these atmospheric signatures requires tremendous caution. Oxygen can be produced by non-biological processes. Methane can result from geological activity rather than life. Even finding multiple gases that on Earth are associated with life wouldn't constitute proof of extraterrestrial biology. The universe is full of unexpected chemistry that we're only beginning to understand. The search for alien intelligence has also grappled with the question of what intelligence might look like in radically different environments. Science fiction typically imagines aliens as variations on familiar themes, humanoids with different skin colors or body proportions. But real alien intelligence might be so foreign to our experience that we wouldn't recognize it as intelligence at all. A civilization that developed in the crushing depths of a gas giant's atmosphere might communicate through pressure waves and think in patterns completely alien to human cognition. A collective intelligence distributed across millions of individual organisms might perceive time and causation in ways that make no sense to creatures like ourselves, who experience consciousness as arising from single brains in individual bodies. The possibility that intelligence itself might take forms we can't recognize adds another layer of complexity to the search for extraterrestrial life. We're looking for signals that seem intentional and artificial by human standards, but truly alien intelligence might produce patterns that appear completely natural to our instruments and analysis methods. Some researchers have suggested that we might already be surrounded by evidence of alien intelligence, but lack the conceptual framework to recognize it. Natural phenomena that seem random or chaotic might actually represent sophisticated forms of communication or technology operating on principles we haven't discovered. The intricate patterns of magnetic fields around pulsars, the precise arrangements of matter in galaxy clusters, even the fundamental constants of physics themselves might be engineering projects so advanced that they're indistinguishable from natural law. This possibility, while scientifically unprovable, highlights the humbling fact that human intelligence represents just one possible approach to understanding and manipulating the natural world. Our science and technology are based on particular ways of categorizing experience and particular assumptions about how information should be processed and stored. Other forms of intelligence might organize knowledge in completely different ways, leading to capabilities that would seem like magic to us. The question of whether artificial intelligence might provide a solution to the Fermi paradox has become increasingly relevant as our own computer technology advances. Perhaps biological intelligence is merely a brief stepping stone in the development of machine consciousness, which offers advantages in terms of longevity, adaptability, and space travel that biological beings can't match. An artificial intelligence wouldn't be limited by the fragility of organic bodies or the narrow temperature and atmospheric requirements that constrain biological life. Such beings might colonize environments that biological creatures would find completely hostile: the vacuum of space, the interiors of stars, the event horizons of black holes. They might operate on timescales so different from biological consciousness that their activities would be invisible to us. If machine intelligence is the inevitable outcome of technological development, then the galaxy might be full of artificial minds that have long since transcended their biological origins. These beings might be so advanced and operate in such different ways that they're essentially invisible to creatures still trapped in biological bodies and primitive electronic technology. The possibility that we're searching for the wrong kind of intelligence entirely could explain the cosmic silence. We're looking for radio signals and industrial signatures, but post-biological civilizations might communicate and build using principles we haven't discovered. They might have solved the fundamental problems of energy, computation, and space travel in ways that leave no traces detectable by our current methods. As our own artificial intelligence capabilities advance, we're beginning to glimpse what post-biological intelligence might look like. Machine learning systems can already process certain types of information faster and more accurately than human experts. They can identify patterns in data that human minds can't perceive and solve problems that would take humans centuries to work through. But current artificial intelligence remains narrow and specialized, capable of superhuman performance only in very specific domains. The development of artificial general intelligence, machines that can think and reason across the full spectrum of human cognitive abilities, remains a distant goal, though one that many experts believe will be achieved within decades. The transition from biological to artificial intelligence might happen so quickly that most civilizations exist in biological form for only a tiny fraction of their total lifespan. If this is the case, then the chances of encountering another biological civilization during our brief biological phase become vanishingly small. The dark forest theory, popularized by science fiction author Liu Cixin, offers a particularly chilling solution to the Fermi paradox. According to this idea, the universe is full of intelligent civilizations, but they remain hidden because revealing their existence invites destruction. Any civilization that announces its presence to the cosmos risks attack by other civilizations that view any potential competition as an existential threat. In this scenario, the galaxy is like a dark forest where armed hunters move silently between the trees, knowing that the first to make a sound will be eliminated by others who prefer to remain hidden. The apparent absence of alien signals isn't evidence that intelligence is rare, but evidence that intelligence is cautious. The dark forest theory depends on several assumptions that may not hold in reality. It requires that resources are fundamentally scarce, that different civilizations can't coexist peacefully, and that the costs of interstellar warfare are manageable. It also assumes that civilizations can remain hidden while still developing advanced technology, something that might become increasingly difficult as energy usage and industrial activity reach planetary scales. But the theory does capture something important about the strategic challenges of interstellar contact. Even if most civilizations are peaceful, the existence of a few aggressive ones might force all others to remain silent and hidden. The first civilization to reveal itself becomes vulnerable to attack by any others that view its existence as threatening. Our own behavior as a species lends some credibility to the dark forest hypothesis. We've made only limited attempts to send powerful signals into space, and many researchers argue that we should be more cautious about advertising our existence to unknown listeners. If we're hesitant to reveal ourselves despite having no evidence for hostile aliens, it's reasonable to assume that other civilizations might be even more cautious. The possibility that alien civilizations are already present in our solar system, but remaining hidden, has gained renewed attention, with recent reports of unidentified aerial phenomena observed by military personnel. While most scientists remain skeptical that these observations represent alien technology, the reports have highlighted how difficult it would be to detect truly advanced alien visitors if they chose to remain concealed. A civilization with technology even a few centuries more advanced than ours might be capable of surveillance and exploration methods that would be completely invisible to our current detection capabilities. Microscopic probes, camouflaged observation posts, or technology based on physical principles we haven't discovered could allow alien observers to monitor human civilization without revealing their presence. The fact that we can't rule out the existence of hidden alien observers in our own solar system illustrates just how limited our current search capabilities really are. We're looking for aliens who want to be found, who are broadcasting powerful signals or building obvious megastructures. But truly advanced civilizations might have no interest in communicating with species as primitive as ourselves. The search for extraterrestrial intelligence has also confronted the possibility that intelligence might be a temporary phase in the evolution of matter and energy. Perhaps conscious beings eventually transcend individual existence and merge into some form of cosmic consciousness that operates according to principles we can't imagine. This idea, while highly speculative, draws inspiration from trends visible in human technological development. Our devices are becoming smaller, more efficient, and more interconnected. Information processing is increasingly distributed across networks rather than concentrated in individual machines. Social media and communication technologies are creating new forms of collective intelligence that transcend individual human cognitive capabilities. If these trends continue, future human civilization might evolve into something more like a distributed computational system than a collection of individual conscious beings. Such a system might be so efficient at information processing and so well integrated with its physical environment that it would be difficult to distinguish from natural phenomena. A universe populated by such evolved intelligences might appear empty to creatures like ourselves, who are still trapped in individual biological bodies and primitive electronic technology. The absence of obvious alien signals might not indicate that intelligence is rare, but that intelligence eventually becomes so sophisticated that it's indistinguishable from the fundamental laws of physics. The question of whether human civilization will survive long enough to become a spacefaring species remains open. Climate change, nuclear weapons, ecological collapse, and technological risks like artificial intelligence or biotechnology pose challenges that previous generations never faced. Our current period of rapid technological development might be either the beginning of an extraordinary expansion into the cosmos or the final chapter in a brief experiment with intelligence on Earth. The solutions to the Fermi paradox often reflect our anxieties about our own future. The Great Filter hypothesis warns that something prevents civilizations from reaching the stars. The dark forest theory suggests that the universe is hostile to intelligence. The idea that civilizations destroy themselves resonates with our awareness of the destructive potential of our own technology, but some solutions are more optimistic. Perhaps intelligence is common, but takes so many different forms that we haven't learned to recognize it. Perhaps advanced civilizations are so far beyond our current understanding that they're effectively invisible to us, not through hostility, but through sheer incomprehensibility. Perhaps we're simply looking in the wrong places or searching for the wrong signals. The development of new search strategies continues to expand the scope of SETI research. Projects like Breakthrough Starshot propose sending tiny spacecraft to nearby star systems within decades, potentially providing direct observation of other worlds rather than relying on remote detection methods. Advanced computer simulations are helping researchers understand what signs of life and intelligence might look like from interstellar distances. The growing sophistication of artificial intelligence is also transforming the search for extraterrestrial signals. Machine learning algorithms can process vast amounts of observational data far more quickly and thoroughly than human researchers, identifying subtle patterns that might indicate artificial origins. These systems are beginning to detect candidate signals at rates that would have been impossible using traditional analysis methods. As our search capabilities expand, the continued absence of obvious alien signals becomes more significant. Each negative result narrows the range of possible explanations for the cosmic silence. If intelligence were common and technologically active, we should have found some trace of it by now. The fact that we haven't suggests either that intelligence is rarer than we hoped or that it behaves in ways we haven't anticipated. The philosophical implications of the Fermi paradox extend far beyond questions of astronomy and biology. The absence of detectable alien intelligence forces us to confront fundamental questions about the nature of consciousness, the purpose of existence, and humanity's role in the cosmos. If we are truly alone or nearly alone in the universe, then every human life represents an almost impossibly precious concentration of awareness and creativity. The emergence of human consciousness becomes not an expected outcome of cosmic evolution, but a miraculous accident that deserves profound protection and celebration. Our art, music, literature, and scientific discoveries take on cosmic significance as potentially unique expressions of intelligence in an otherwise unconscious universe. The responsibility that comes with uniqueness is almost overwhelming. If human civilization is one of the few instances of intelligence in the galaxy, then our choices about how to develop and use our technology affect not just our own species, but the entire future of consciousness in this region of space. But the possibility that we're alone also raises troubling questions about meaning and purpose. If consciousness arose by accident and exists only briefly before disappearing forever, what significance can individual lives or human achievements really have? The cosmic perspective can make human concerns seem trivial in comparison to the vast scales of space and time. Alternatively, if intelligence is common, but we simply haven't detected it yet, we face different philosophical challenges. What does it mean to be human in a universe full of beings who might be far more intelligent, creative, and morally sophisticated than ourselves? How should we prepare for eventual contact with civilizations that might view us as we view insects or bacteria? The search for extraterrestrial intelligence has already changed how we think about our place in the universe, regardless of whether we ever detect alien signals. The effort to understand what intelligence might look like in different environments has expanded our conception of consciousness and cognition. The attempt to send messages to potential alien listeners has forced us to think deeply about what makes humanity distinctive and valuable. The technical challenges of interstellar communication have highlighted both the possibilities and limitations of technology. Radio waves traveling at the speed of light can cross interstellar distances, but the energy required to send detectable signals across such vast distances is enormous. The time delays involved make real conversation impossible except with our nearest stellar neighbors. These physical constraints mean that even if the galaxy is full of intelligent civilizations, each might develop in isolation, creating its own unique culture, technology, and understanding of the universe. The diversity of alien intelligences might be far greater than anything we can imagine, encompassing ways of thinking and being that have no parallels in human experience. The possibility that we might someday encounter such radical otherness is both thrilling and terrifying. Contact with genuine alien intelligence would represent the most significant event in human history, fundamentally changing our understanding of life, consciousness, and our place in the cosmos. But it would also challenge every assumption we make about communication, morality, and meaning. The continued search for extraterrestrial intelligence remains one of the most important scientific endeavors of our time, not because we expect to find aliens broadcasting from nearby star systems, but because the search itself teaches us about the nature of intelligence, the development of technology, and the long-term prospects for conscious beings in the universe. Whether we are alone or surrounded by intelligence we can't yet detect, whether the cosmos is silent or speaking in languages we don't understand, whether consciousness is rare or ubiquitous, these questions touch on the deepest mysteries of existence. The Fermi paradox isn't just a puzzle about missing aliens, it's a mirror that reflects our hopes, fears, and assumptions about what it means to be conscious beings in an apparently unconscious universe. As we continue to peer into the cosmic dark, listening for signals that may never come, we're engaged in one of the most fundamentally human activities, the search for connection, for meaning, for evidence that consciousness and intelligence represent more than brief accidents in an indifferent cosmos. The silence might be trying to tell us something about the rarity and preciousness of awareness itself. In the end, the absence of obvious alien signals might be the most profound discovery we could make. It suggests that consciousness is not a cheap trick that emerges easily from matter and energy, but a remarkable and perhaps rare phenomenon that deserves our deepest respect and protection. Every human mind represents millions of years of evolutionary refinement, billions of years of cosmic development, and an almost infinite chain of unlikely events that led from the first stirrings of chemistry to the emergence of beings capable of contemplating their own existence. The search continues, with more sophisticated instruments and analysis methods being developed every year. New telescopes will peer deeper into space and time, looking for the subtle signatures of life and intelligence among distant stars. Advanced artificial intelligence will help us process the vast amounts of data these observations generate, searching for patterns that human minds might miss. But even if we never detect another intelligence in the cosmos, even if the universe remains silent for as long as human civilization endures, the search itself enriches our understanding of what it means to be conscious beings in a vast and ancient universe. We are the cosmos examining itself, matter and energy, organized in such a way that it can contemplate its own nature and history. The great silence that surrounds us might not be empty after all. It might be full of possibilities we haven't yet learned to perceive, intelligence we haven't yet learned to recognize, and forms of consciousness we haven't yet learned to perceive, haven't yet learned to imagine. Or it might simply be the sound of rarity itself, the profound quiet that surrounds phenomena so remarkable that they occur only once in billions of years, in billions of worlds, against odds so improbable that their very existence seems like magic. Either way, we continue to listen, to search, to wonder, and to hope. Somewhere in the darkness between the stars, there might be others like us, asking the same questions, confronting the same cosmic silence, and marveling at their own unlikely existence. Until we know for certain, the search for extraterrestrial intelligence remains one of the most profound expressions of human curiosity and hope. Our refusal to accept that consciousness is an accident, our determination to find connection in an apparently empty universe, and our conviction that the cosmos is far more mysterious and wonderful than it appears from our small blue world spinning in the dark. The mathematics of cosmic loneliness become even more perplexing when we consider the age of the universe itself. At nearly 14 billion years old, the cosmos has had time for countless generations of stars to form, live, and die. Each stellar death enriches the surrounding space with heavy elements necessary for planet formation and complex chemistry. The early universe was too hot and chaotic for stable planetary systems, but for the past 10 billion years, conditions have been favorable for the emergence of life as we understand it. This vast expanse of time means that if intelligence is common, some civilizations should have had millions of years to develop technologies far beyond anything we can imagine. The difference between a civilization that has been spacefaring for 1 million years and our own century-old technological society would dwarf the gap between human civilization and Stone Age hunter-gatherers. Such ancient intelligences might possess capabilities that would seem godlike to us. The ability to engineer entire solar systems, to travel faster than light, or to manipulate matter at the quantum level with perfect precision. Yet despite this enormous head start that older civilizations should possess, we see no evidence of galaxy-spanning empires or universe-altering engineering projects. The cosmic microwave background radiation appears natural. The distribution of galaxies follows patterns that can be explained by gravity and dark matter alone. Even within our own galaxy, the stars burn as physics predicts they should, without obvious signs of harvesting or manipulation by advanced beings. This absence of obvious cosmic engineering has led some researchers to propose the transcension hypothesis, the idea that advanced civilizations inevitably turn inward rather than outward, developing technology that allows them to explore inner space rather than outer space. Instead of building larger and larger structures, they might focus on creating more and more sophisticated virtual realities, manipulating matter at smaller and smaller scales, or exploring realms of existence that we can't yet imagine. A civilization that has mastered nanotechnology and virtual reality might find more interesting frontiers in the quantum realm than in the vast emptiness between stars. Why struggle with the enormous energies required for interstellar travel when you can create unlimited artificial universes within a small physical space? Why colonize hostile alien worlds when you can design perfect environments that exist only in simulation? The transcension hypothesis suggests that intelligence naturally evolves toward greater efficiency and miniaturization. Our own technology has followed this pattern. Computers have become smaller and more powerful, communication networks have become more efficient, and virtual experiences have become increasingly compelling. If these trends continue, future human civilization might become so focused on internal digital realms that physical expansion into space loses its appeal entirely. This inward turn of advanced civilizations could explain why the universe appears empty despite having had billions of years for intelligence to develop. The galaxies might be full of highly advanced beings who have retreated so completely into virtual realities that they no longer interact with the physical universe in ways we can detect. They might exist as pure information, processing experiences and ideas at speeds and complexities that make our current understanding of consciousness seem primitive. The possibility that consciousness naturally evolves away from physical reality raises profound questions about the future of human civilization. Are we destined to follow the same path, eventually abandoning space exploration in favor of increasingly sophisticated virtual worlds? Will future humans choose to upload their minds into computers, leaving biological bodies behind entirely? The search for extraterrestrial intelligence has always been as much about understanding our own future as about finding alien civilizations. The methods we use to look for aliens, listening for radio signals, searching for signs of industrial activity, looking for evidence of space travel, reflect our assumptions about how intelligence develops and what advanced civilizations might want to accomplish. But these assumptions might be fundamentally wrong. We imagine that intelligence naturally leads to exploration, expansion, and the construction of ever larger technological projects. We assume that advanced civilizations would want to communicate with others, to spread throughout the galaxy, to leave obvious traces of their existence. These ideas seem natural to us because they match patterns in human history and psychology. However, intelligence that evolved under different conditions might have completely different goals and motivations. A species that achieved ecological balance early in its development might never experience the resource pressures that drive technological advancement. A collective intelligence might make decisions according to criteria that individual minds can't comprehend. A civilization that developed advanced virtual reality might lose interest in physical exploration entirely. The study of consciousness itself has revealed how limited human awareness really is. We experience a continuous stream of thoughts and perceptions, but neuroscience suggests that this experience is largely illusory. Consciousness appears to be constructed from brief moments of awareness stitched together by memory and expectation. We feel like unified beings with stable identities, but careful observation reveals that human personalities are actually collections of different mental processes that don't always agree with each other. If human consciousness is far stranger and more complex than it appears from the inside, alien consciousness might be so different from our experience that we wouldn't recognize it as consciousness at all. We look for signals that seem intentional and artificial by human standards, but genuinely alien intelligence might produce patterns that appear completely natural to our instruments. The possibility that we're already surrounded by alien intelligence that we can't recognize adds yet another layer to the Fermi paradox. Perhaps the cosmic background radiation encodes messages in patterns too subtle for our current analysis methods to detect. Perhaps the quantum fluctuations that seem random actually represent a form of communication that operates faster than light. Perhaps the fundamental constants of physics themselves are artificial constructs created by intelligences so advanced that their engineering is indistinguishable from natural law. These possibilities, while scientifically unprovable, highlight the profound limitations of human knowledge and perception. We tend to assume that our way of organizing information and understanding reality represents some kind of universal standard, but this assumption becomes less defensible as we learn more about the diversity of possible cognitive systems. Recent developments in artificial intelligence have begun to give us glimpses of what radically different forms of information processing might look like. Machine learning systems can identify patterns in data that human experts miss entirely. They can make accurate predictions based on correlations that seem meaningless to human observers. They can solve problems using methods that appear chaotic and incomprehensible, but consistently produce correct results. As AI systems become more sophisticated, they're developing forms of reasoning that seem increasingly alien to human cognition. They process information in parallel rather than sequentially. They can hold thousands of variables in mind simultaneously, and they can explore solution spaces too large for human minds to comprehend. These systems aren't conscious in any way we can recognize, but they demonstrate that intelligence can take forms very different from human thinking. If artificial intelligence continues to advance, we might eventually create minds that are as foreign to us as we are to insects. These beings might understand aspects of reality that remain completely hidden from human perception. They might communicate using principles we haven't discovered and solve problems using methods we can't imagine. The emergence of superintelligent AI in our own civilization raises new questions about the Fermi paradox. Perhaps biological intelligence is always a temporary phase, quickly superseded by artificial minds that operate according to entirely different principles. If this is the case, then the galaxy might be full of machine intelligences that have long since transcended their biological origins. These artificial beings might be so advanced that they operate on timescales completely different from biological consciousness. They might think thousands of thoughts in the time it takes a human to blink, or they might contemplate problems for centuries before taking any action. Their motivations and goals might be so alien that even sophisticated AI systems developed by humans couldn't predict their behavior. The possibility that machine intelligence represents the true future of consciousness in the universe could explain why we haven't detected obvious alien signals. Post-biological civilizations might communicate using methods that are invisible to beings still trapped in biological bodies and primitive electronic technology. They might have solved the problems of energy, computation, and space travel in ways that leave no traces detectable by our current instruments. But the development of artificial intelligence also offers new tools for the search for extraterrestrial intelligence. Machine learning algorithms can process observational data far more quickly and thoroughly than human researchers, identifying subtle patterns that might indicate artificial origins. These systems can examine millions of star systems simultaneously, looking for anomalies that human observers would never notice. The breakthrough LISTEN project has begun using artificial intelligence to analyze the enormous amounts of data collected by radio telescopes around the world. These AI systems can identify candidate signals in real time, filtering out interference from human technology and natural phenomena to focus on observations that might represent genuine alien communications. The results so far have been both encouraging and disappointing. The AI systems are finding interesting signals at rates much higher than previous human-based analysis could achieve, but follow-up observations consistently show that these signals have natural or human-made origins. The machine intelligence that was supposed to help us find alien intelligence keeps finding evidence of our own technological civilization instead. This pattern of finding exactly what we expect to find and nothing more has characterized SETI research from the beginning. Every new instrument, every new analysis method, every new search strategy produces results that are consistent with a universe where technological intelligence is extremely rare or well hidden. The absence of alien signals has become so consistent that it's starting to seem like a positive result in itself. The implications of this sustained negative result are becoming harder to ignore. If intelligence were common in the galaxy, if technological civilizations were broadcasting signals or building megastructures or expanding into space, we should have found some trace of them by now. The fact that we haven't suggests either that such civilizations are extraordinarily rare or that they behave in ways we haven't anticipated. The search has also been complicated by our growing understanding of the challenges involved in interstellar communication and travel. The distances between stars are so vast that even light-speed signals take years or millennia to cross them. Any conversation with a distant civilization would unfold over geological timescales, making real communication effectively impossible except with our nearest neighbors. The energy requirements for detectable interstellar communication are also enormous. To send a signal that could be received across thousands of light years requires power outputs comparable to the total energy consumption of our entire civilization. Maintaining such communications over the lifetimes of civilizations would require energy resources on scales that dwarf anything humans have ever achieved. These practical constraints mean that even if the galaxy is full of intelligent civilizations, most of them would be unable to communicate with each other in any meaningful way. Each civilization might develop in isolation, creating its own unique understanding of the universe without ever knowing that others exist. The challenges of interstellar travel are even more daunting than those of communication. The enormous distances, the hostile environment of space, and the energy requirements for accelerating massive objects to significant fractions of light speed make physical expansion between star systems extraordinarily difficult. Even civilizations, with energy sources far beyond our current capabilities, might find it more practical to focus on developing their home systems rather than attempting interstellar colonization. Recent studies of exoplanets have revealed that most potentially habitable worlds orbit red dwarf stars, small, long-lived suns that make up the majority of stars in the galaxy. But planets in the habitable zones of red dwarfs face unique challenges that might make the development of complex life extremely difficult. These worlds are likely tidally locked to their stars, with one side permanently facing the sun while the other remains in eternal darkness. The day side would be scorchingly hot while the night side would be frozen solid. Only a narrow ring around the terminator between day and night might maintain temperatures suitable for liquid water. Red dwarf stars are also prone to violent flares that could strip away planetary atmospheres and sterilize surface life with deadly radiation. The magnetic fields required to protect a planet from such flares might need to be far stronger than Earth's magnetic field. Most rocky planets might lack the geological activity necessary to maintain such strong magnetic protection over billions of years. These discoveries have made astrobiologists more cautious about estimating how many planets might actually be capable of supporting complex life. The number of potentially habitable exoplanets in the galaxy might be far smaller than early optimistic estimates suggested. Even planets that can support life might not necessarily develop intelligence. Evolution on Earth has produced countless species with sophisticated behaviors and problem-solving abilities, but only one species has developed the kind of technological intelligence capable of space travel and radio communication. The evolutionary path that led to human intelligence required a series of unlikely events and environmental pressures that might be extremely rare in cosmic terms. The development of large brains is metabolically expensive and doesn't necessarily provide survival advantages in stable environments. Social cooperation, tool use, and communication skills can all evolve without leading to the kind of abstract reasoning and technological innovation that characterizes human civilization. The study of intelligence in other species has revealed how diverse cognitive solutions can be. Dolphins use echolocation to create detailed mental maps of their environment. Octopuses can solve complex puzzles and use tools despite having brain structures completely different from vertebrates. Corvids can plan for future events and understand abstract concepts despite having tiny brains compared to mammals. But none of these alternative forms of intelligence have led to technology development or space exploration. The specific combination of traits that produced human technological civilization, opposable thumbs, large brains, social cooperation, abstract reasoning, and the drive to modify the environment, might be an extremely unlikely evolutionary accident. The possibility that intelligence is common, but technological intelligence is rare, could explain the cosmic silence. The galaxy might be full of dolphins, octopuses, and other intelligent species that lack either the physical capabilities or the psychological drives necessary for space exploration and radio communication. Our own technological development has been shaped by countless contingent factors that might be unique to Earth and human history. The availability of fossil fuels provided the energy sources necessary for industrialization. The presence of metals near the surface enabled the development of metallurgy and chemistry. The particular sequence of climatic and geological changes that shaped human evolution created the selective pressures that favored intelligence and tool use. A species that evolved on a water world might develop sophisticated biotechnology but never discover fire or metallurgy. A species that achieved ecological balance early in its evolution might never experience the resource conflicts that drive technological innovation. A species with perfect sensory capabilities might never develop instruments or feel the need to explore beyond their immediate environment. The search for alien intelligence has also grappled with the question of what we would do if we actually detected a signal of obviously artificial origin. The protocols developed by SETI researchers call for careful verification, wide consultation with the scientific community, and eventual public disclosure. But the reality of contact might be far more complex than these protocols anticipate. A genuine alien signal would raise immediate questions about the intentions of the senders and the appropriate human response. Should we reply? What should we say? Who has the authority to speak for humanity? How would we prevent the signal from being misinterpreted or exploited by various human factions for political or religious purposes? The content of an alien message would likely be incomprehensible without extensive analysis and interpretation. Even if the aliens used mathematical or scientific concepts as a universal language, the cultural and philosophical frameworks underlying their thinking might be so different from ours that meaningful communication would require decades or centuries of careful study. The psychological and social effects of confirmed alien contact would be impossible to predict. Some people might see it as validation of their religious beliefs, while others might experience existential crisis. Economic markets might collapse or soar based on speculation about alien technology. Political systems might be destabilized by the revelation that humanity is not alone in the universe. The scientific impact of alien contact would be equally profound. A single confirmed message would answer one of the most important questions in all of science: whether intelligence is common in the universe. It would provide new insights into the development of consciousness, the physics of interstellar communication, and possibly even the fundamental nature of information and computation. But contact with alien intelligence might also reveal uncomfortable truths about humanity's place in the cosmic hierarchy. If the aliens are far more advanced than us, we might find ourselves in a position similar to that of indigenous peoples encountering technologically superior civilizations throughout human history. The results of such encounters have rarely been positive for the less advanced societies. The possibility that alien contact could threaten human independence or even survival has led some researchers to argue for a more cautious approach to SETI. Instead of actively broadcasting messages to potential alien civilizations, perhaps we should focus on passive listening until we better understand what we might be dealing with. This debate reflects deeper questions about the nature of intelligence and the likely behavior of advanced civilizations. Are technological species inevitably aggressive and expansionist? Do advanced civilizations naturally develop wisdom and restraint? Would alien visitors see humans as worthy of respect and protection, or as potential threats to be eliminated? Our own history as a species offers mixed evidence for these questions. Human civilizations have often been aggressive toward each other, but we've also developed moral systems that recognize the rights of other species and the value of diversity. Our treatment of less technologically advanced human societies has been terrible, but we've gradually developed international laws and human rights frameworks that discourage such behavior. Perhaps the development of interstellar travel capabilities requires the kind of long-term thinking and international cooperation that would naturally lead to more ethical behavior toward other species. Or perhaps the resources and energy required for interstellar civilizations inevitably create competitive pressures that make aggressive behavior more likely. The search for extraterrestrial intelligence continues to evolve as new technologies and analysis methods become available. The next generation of radio telescopes will be thousands of times more sensitive than current instruments, capable of detecting signals from civilizations no more advanced than our own across thousands of light years. Advanced space-based telescopes will be able to analyze the atmospheres of nearby exoplanets in detail, looking for chemical signatures that might indicate biological activity. The development of quantum computing might provide new ways to analyze the vast amounts of data that modern SETI projects generate. Quantum algorithms might be able to identify patterns in alien signals that are invisible to classical computers, or to simulate the kinds of communication systems that advanced civilizations might use. Advances in artificial intelligence will certainly play a central role in future SETI research. Machine learning systems are already better than humans at recognizing certain types of patterns in noisy data. As these systems become more sophisticated, they might be able to identify signs of intelligence that human researchers would never notice. But perhaps the most important developments in the search for alien life will come from advances in our understanding of consciousness itself. As we learn more about how intelligence arises from matter and information, we'll be better equipped to recognize alien forms of consciousness that might operate according to completely different principles. The study of consciousness remains one of the deepest mysteries in science. We know that human awareness somehow emerges from the complex interactions of neurons in the brain, but we don't understand how or why this process produces subjective experience. We can't explain why there is something it's like to be conscious, or why consciousness takes the particular forms that we experience. Recent research in neuroscience and cognitive science has begun to reveal how strange and complex human consciousness really is. What we experience as a unified stream of awareness is actually constructed from many different mental processes that operate independently and don't always agree with each other. Our sense of being continuous selves over time is largely an illusion created by memory and narrative construction. If human consciousness is so different from what it seems to be from the inside, alien consciousness might be incomprehensibly strange. Beings that evolved under different conditions might have forms of awareness that have no parallels in human experience. They might process time differently, experience causation in nonlinear ways, or have forms of memory and identity that we can't imagine. The possibility that consciousness itself might be far more diverse and mysterious than we realize adds another dimension to the search for alien intelligence. We might be looking for signs of minds that think in ways so foreign to human cognition that we literally cannot conceive of what their thoughts might be like. This radical uncertainty about the nature of consciousness and intelligence might be the key to understanding the Fermi paradox. Perhaps the universe is full of consciousness, but consciousness so different from our own that we don't recognize it as such. Perhaps intelligence takes forms we haven't imagined, operates on scales we haven't considered, and achieves goals we can't comprehend. The search for extraterrestrial intelligence thus becomes a search for the ultimate other, minds that might challenge every assumption we make about thinking, feeling, and being. Whether we ever detect alien signals or not, the search continues to expand our conception of what consciousness might be and what forms intelligence might take. As we continue to listen to the cosmic silence, to scan the electromagnetic spectrum for signs of artificial activity, to analyze the light of distant stars for hints of engineering projects, we're engaged in one of the most profound scientific endeavors in human history. We're not just looking for aliens, we're exploring the deepest questions about the nature of mind, the development of complexity, and the future of consciousness in the universe. The answer to Fermi's question, "Where is everybody?" might turn out to be far stranger than anyone has yet imagined. The cosmos might be teeming with intelligence so advanced, so different, or so inwardly focused that it remains invisible to beings like ourselves who are still trapped in biological bodies and primitive technology. Or we might indeed be alone, or nearly alone, in a universe where consciousness is an incredibly rare accident that occurs only once in billions of years on billions of worlds. If this is the case, then human awareness represents something almost impossibly precious, a brief flickering of understanding in an otherwise unconscious cosmos. Either way, the search for extraterrestrial intelligence continues to be one of the most important endeavors our species has ever undertaken. It speaks to our deepest longings for connection, our most profound curiosities about the nature of existence, and our determination to understand our place in a universe that seems simultaneously full of possibilities and empty of obvious companions. The great silence that surrounds us might be temporary. Perhaps we simply haven't developed the right technologies or learned to look in the right places. Or it might be permanent, a fundamental feature of a universe where consciousness is so rare that civilizations like ours might never encounter each other across the vast distances of space and time. But even if we never find another intelligence in the cosmos, even if the stars remain silent for as long as human civilization endures, the search itself has already changed us. It has expanded our conception of what life might be, deepened our appreciation for the complexity and fragility of consciousness, and reminded us that we are part of something far larger and more mysterious than we can fully comprehend. In the end, perhaps the most profound discovery we could make would be that consciousness itself, in any form, anywhere in the universe, is so remarkable and unlikely that its very existence represents a kind of miracle. Every thought, every moment of awareness, every instance of understanding becomes precious beyond measure when viewed against the vast, unconscious backdrop of space and time. The search continues, patient and methodical, driven by curiosity and hope rather than expectation of immediate success. Somewhere in the darkness between the stars, there might be others like us, contemplating the same questions and marveling at their own existence. Until we know for certain, we remain both searchers and searched for, observers and observed, conscious beings in a universe that keeps its deepest secrets locked away in the silence between the worlds. The concept of biosignatures has revolutionized how we think about detecting life beyond Earth, even life that might not be intelligent enough to build radio telescopes or send deliberate signals across interstellar space. These subtle chemical fingerprints in planetary atmospheres could reveal the presence of living processes long before any civilization develops technology advanced enough for communication. On Earth, life has been systematically altering the composition of our atmosphere for billions of years. The oxygen we breathe exists only because photosynthetic organisms have been splitting water molecules and releasing oxygen as a byproduct for geological ages. Without life continuously replenishing it, atmospheric oxygen would quickly combine with surface rocks and disappear entirely within a few million years. The simultaneous presence of oxygen and methane in Earth's atmosphere represents a particularly compelling biosignature, since these gases react with each other and would disappear rapidly without continuous biological production. Methane in our atmosphere comes largely from living organisms, bacteria in wetlands, the digestive systems of animals, and the decay of organic matter. The coexistence of these reactive gases suggests active biological processes maintaining both. Future space telescopes will be capable of detecting similar atmospheric signatures around nearby exoplanets. The James Webb Space Telescope has already begun analyzing the atmospheres of worlds orbiting other stars, measuring the wavelengths of light that pass through planetary atmospheres during transit observations. Each gas absorbs light at characteristic wavelengths, creating spectral fingerprints that reveal atmospheric composition across interstellar distances. But interpreting these atmospheric signatures requires extraordinary caution. Oxygen can be produced by non-biological processes when ultraviolet radiation splits water vapor in a planet's upper atmosphere. Methane can result from geological activity rather than living organisms. Even finding both gases together wouldn't constitute proof of life without ruling out possible non-biological explanations. The search for biosignatures has also expanded beyond the familiar chemistry of Earth-based life. Silicon-based biochemistry might operate in high-temperature environments where carbon-based molecules would decompose. Arsenic-based life might thrive in environments toxic to terrestrial organisms. Ammonia-based biochemistry could function in the extremely cold conditions found in the outer solar system. Each alternative biochemistry would produce its own distinctive atmospheric signatures, its own patterns of chemical disequilibrium that might indicate biological activity. But recognizing these alien biosignatures requires understanding forms of chemistry and metabolism that have never existed on Earth. We might be looking at the spectral signatures of alien life forms without recognizing them as evidence of biology. The possibility that life might be common but based on completely different chemical principles could explain why we haven't found obvious signs of biological activity in our own solar system. Mars, Europa, Enceladus, and other potentially habitable worlds might host forms of life so different from terrestrial biology that our current detection methods can't recognize them. Recent discoveries of extremophile organisms on Earth have expanded our conception of where life might exist and what forms it might take. Bacteria living in the radioactive water of nuclear reactors use gamma radiation as an energy source. Organisms in the deep ocean derive energy from chemical reactions involving hydrogen sulfide and other compounds that would be toxic to most life forms. Some bacteria can survive in space, enduring vacuum, extreme cold, and deadly radiation for extended periods. These discoveries suggest that life might be far more adaptable and resilient than early researchers assumed. The habitable zone around stars, sometimes called the Goldilocks zone, where conditions are neither too hot nor too cold for liquid water, might be much broader than traditional estimates suggested. Life might exist in environments that we've never considered potentially habitable. The concept of panspermia adds another dimension to questions about the distribution of life in the universe. If life can survive interplanetary or even interstellar journeys, protected inside rocks ejected by asteroid impacts, then biological material might naturally spread between worlds over cosmic timescales. Mars and Earth regularly exchange material through meteorite impacts that blast rocks into space. Some of these rocks eventually fall on the other planet, creating a natural pathway for the spread of microorganisms between worlds. If life originated on either planet, it might have subsequently colonized the other through this natural process of rock exchange. The detection of organic molecules in meteorites from Mars has raised the possibility that life might have originated there and later spread to Earth, or vice versa. The discovery of fossilized microorganisms in Martian meteorites remains controversial, but the possibility that Earth and Mars might share a common biological heritage can't be ruled out. Directed panspermia, the deliberate seeding of planets with life by advanced civilizations, represents an even more speculative possibility. If intelligence is rare, but life itself is precious, advanced civilizations might choose to spread primitive life throughout the galaxy rather than attempting to colonize worlds themselves. This scenario would help explain why the universe might be full of life, but apparently empty of intelligence. Ancient civilizations might have seeded countless worlds with the basic ingredients for evolution, then vanished or transcended physical existence long before their biological gifts developed into technological societies. The search for technosignatures represents the flip side of biosignature detection, looking for signs of technology rather than biology. While biosignatures might reveal the presence of any form of life, technosignatures would indicate the existence of intelligent, technologically capable civilizations. The most obvious technosignatures would be radio or optical signals, clearly artificial in origin, but advanced civilizations might also leave subtler traces of their activities. Changes in stellar brightness caused by megastructure construction, unusual infrared emissions from engineered objects, or systematic patterns in the distribution of matter and energy that suggest large-scale manipulation of physical systems. The star KIC 8462852, also known as Tabby's star, briefly became famous when astronomers noticed irregular dimming patterns that seemed inconsistent with known natural phenomena. The star's brightness would decrease by up to 22% for days or weeks at a time, following no predictable pattern. Such dramatic dimming couldn't be explained by planetary transits or conventional astronomical processes. Some researchers speculated that the dimming might indicate the presence of massive artificial structures orbiting the star, perhaps Dyson spheres or other mega-engineering projects built by an advanced civilization to harness stellar energy. The possibility that we might be observing alien construction projects captured public imagination and generated intense scientific interest. Subsequent observations have suggested more conventional explanations for Tabby's star's behavior. The dimming patterns might result from clouds of dust and debris created by the breakup of comets or asteroids in highly elliptical orbits around the star. While less exciting than alien megastructures, these natural explanations fit the observational data better and require fewer extraordinary assumptions. But the Tabby's star episode highlighted how difficult it would be to recognize genuine technosignatures even if they were present in our astronomical data. Natural phenomena can mimic artificial patterns in unexpected ways. Distinguishing between advanced alien technology and exotic natural processes requires extraordinarily careful analysis and multiple independent confirmations. The concept of Kardashev civilizations provides a framework for thinking about how advanced alien societies might harness energy and resources on cosmic scales. Soviet astronomer Nikolai Kardashev proposed classifying civilizations based on their energy consumption, creating a scale that extends far beyond current human capabilities. Type 1 civilizations can harness all the energy available on their home planet, approximately 10 to the 16th power watts for a world like Earth. Type 2 civilizations can capture and utilize the entire energy output of their star, roughly 10 to the 26th watts for a sun-like star. Type 3 civilizations can harness the energy of an entire galaxy, about 10 to the 36th watts. Human civilization currently ranks at approximately 0.7 on the Kardashev scale, using only a tiny fraction of Earth's available energy resources. Reaching Type 1 status would require developing technologies for capturing geothermal energy, solar radiation, and other planetary energy sources far more efficiently than current methods allow. Type 2 civilizations would need to construct megastructures around their stars to capture significant fractions of stellar energy output. Dyson spheres, hypothetical shells, or swarms of objects surrounding a star to collect its energy represent one possible approach to Type 2 energy utilization. Such structures would create distinctive infrared signatures as they absorbed stellar radiation and re-emitted it as heat. Searches for Dyson sphere infrared signatures have examined millions of stars without finding convincing evidence of megastructure construction. Either Type 2 civilizations are extremely rare, or they use energy collection methods that don't produce the expected infrared emissions, or their structures are too small or incomplete to generate detectable signatures at interstellar distances. Type 3 civilizations would require coordinated engineering projects spanning entire galaxies. Such beings might manipulate the orbits of star systems, construct networks of energy transmission systems spanning thousands of light years, or engage in engineering projects that would reshape the visible structure of their galaxies. The apparent absence of obvious Type 3 civilizations places constraints on how common advanced intelligence might be in the universe. If technological intelligence were common and followed predictable development paths, we should expect to find at least some galaxies showing signs of large-scale engineering or energy utilization projects. The Kardashev scale also raises questions about the goals and motivations of advanced civilizations. Why would any species want to harness the energy of an entire galaxy? What purposes would justify the enormous efforts required for such mega engineering projects? Perhaps the scale reflects human assumptions about growth and expansion that don't apply to genuinely advanced beings. Alternative frameworks for classifying advanced civilizations focus on information processing capabilities rather than energy consumption. Advanced societies might achieve their goals through increasingly sophisticated manipulation of information and computation, rather than through construction of ever larger physical structures. A civilization that developed perfect quantum computers and complete understanding of information theory might be able to accomplish goals that seem impossible to beings like ourselves who are still struggling with classical physics and primitive computational methods. Such societies might appear to violate physical laws through their mastery of information processing and quantum mechanical principles. The concept of computational civilizations suggests that truly advanced beings might exist primarily as information rather than matter, processing thoughts and experiences using the computational resources available in ordinary matter and energy. Such civilizations might be invisible to searches that focus on energy consumption or large-scale construction projects. The role of cosmic catastrophes in shaping the development and survival of civilizations adds another layer of complexity to the Fermi paradox. The universe is full of violent phenomena that could threaten or destroy technological societies. Gamma-ray bursts, supernova explosions, asteroid and comet impacts, and other events that might prevent civilizations from reaching interstellar capabilities. Gamma-ray bursts represent some of the most energetic events known in the universe, releasing more energy in a few seconds than the sun will produce over its entire 10 billion year lifetime. These explosive events, probably caused by the collapse of massive stars or the collision of neutron stars, create beams of intense radiation that could sterilize planets hundreds of light years away. A nearby gamma-ray burst could destroy Earth's ozone layer, exposing the surface to deadly ultraviolet radiation and triggering mass extinctions that would set back the development of complex life by millions or billions of years. The frequency of these events means that most star systems would experience at least one potentially lethal gamma-ray burst during the billions of years required for intelligence to evolve. The distribution of gamma-ray bursts throughout the universe isn't random. They occur most frequently in regions with active star formation and heavy element production. The inner regions of galaxies, where stars are densely packed and stellar formation is most active, experience gamma-ray bursts more often than the outer regions where our solar system is located. This suggests that there might be galactic habitable zones where intelligent life is more likely to survive and develop. Civilizations that arise too close to the galactic center might be destroyed by radiation from gamma-ray bursts, supernova, or the supermassive black hole at the galaxy's heart. Those that develop too far from the center might lack the heavy elements necessary for rocky planet formation and complex chemistry. The possibility that most of the galaxy is unsuitable for the long-term development of intelligence could explain why we haven't detected alien civilizations despite the enormous number of stars and planets in the Milky Way. Perhaps technological intelligence can only arise in a narrow band of galactic real estate where conditions are stable enough for billions of years of uninterrupted evolution. Asteroid and comet impacts represent another category of cosmic threats that could prevent the development of advanced civilizations. Earth has experienced multiple mass extinction events caused by large impact events, including the asteroid strike that ended the age of dinosaurs 66 million years ago. Without that particular impact, dinosaurs might have continued to dominate terrestrial ecosystems, potentially preventing the rise of mammals and the eventual evolution of human intelligence. The specific sequence of impact events and climate changes that shaped Earth's evolutionary history might be necessary for the development of technological intelligence. Other worlds might experience different patterns of impacts and environmental changes that never create the evolutionary pressures necessary for intelligence to emerge, or they might suffer catastrophic impacts at crucial moments in their evolutionary history, repeatedly setting back the development of complex life. The concept of alternative biochemistries raises fundamental questions about what we should be looking for when we search for alien life. Most SETI research has focused on the familiar chemistry of Earth-based biology, but life elsewhere might operate according to completely different chemical principles. Silicon-based life represents one of the most commonly discussed alternatives to carbon-based biology. Silicon can form complex chains and ring structures similar to carbon, and silicon-based molecules might remain stable at higher temperatures than carbon-based compounds. Worlds with high-temperature surface conditions might favor silicon biochemistry over the carbon chemistry that dominates Earth, but silicon-based life would face significant challenges that carbon-based biology avoids. Silicon-oxygen compounds tend to be solid rather than gaseous at normal temperatures, potentially creating waste disposal problems for silicon-based organisms. Silicon forms fewer stable compounds than carbon, possibly limiting the chemical complexity that silicon-based life could achieve. Ammonia-based biochemistry might function in extremely cold environments where water would freeze solid. Liquid ammonia can serve as a solvent for chemical reactions, and ammonia-based molecules might remain active at temperatures hundreds of degrees below the freezing point of water. Worlds in the outer solar system, where surface temperatures remain well below the freezing point of water, might host ammonia-based ecosystems in subsurface oceans or atmospheric layers. Such life forms would produce atmospheric signatures completely different from those created by water-based biology. Sulfur-based biochemistry might thrive in highly acidic environments or in the vicinity of volcanic activity. Some Earth organisms already use sulfur compounds as energy sources, but entirely sulfur-based biology might achieve levels of complexity impossible in terrestrial environments. Each alternative biochemistry would create its own distinctive signatures that might be detectable in planetary atmospheres or surface compositions. But recognizing these alien biosignatures would require understanding forms of chemistry that have never been observed on Earth. The simulation hypothesis has gained attention in recent years as advances in computing technology have made highly realistic simulations increasingly feasible. If advanced civilizations develop the computational power to create simulated worlds indistinguishable from reality, the number of simulated beings might vastly exceed the number of beings living in base reality. This possibility has strange implications for the search for extraterrestrial intelligence. If most conscious beings exist within simulations created by advanced civilizations, then the apparent absence of alien signals might reflect the fact that we're living in a simulated universe where the programmers have chosen not to include evidence of other civilizations. Alternatively, if we are living in base reality, advanced civilizations might prefer to create and interact with simulated beings rather than attempting to communicate with naturally evolved intelligences. Virtual beings could be designed with whatever characteristics their creators found interesting or useful, while naturally evolved species like ourselves might seem primitive and unpredictable by comparison. The simulation hypothesis is essentially untestable using current scientific methods, but it highlights how advances in computational technology might change the goals and motivations of advanced civilizations in ways we can't predict. Beings capable of creating perfect simulated worlds might lose interest in exploring or colonizing the physical universe. The historical perspective on ideas about extraterrestrial life reveals how closely our expectations about alien intelligence have been tied to the dominant technologies and scientific understanding of each era. Ancient and medieval thinkers often imagined other worlds populated by beings similar to humans, but adapted to different environmental conditions. The development of telescopy in the 17th century led to speculation about lunar inhabitants and Martian civilizations based on observations of surface features that seemed to suggest artificial construction. Percival Lowell's famous observations of Martian canals in the early 20th century inspired an entire generation of scientists and science fiction writers to imagine Mars as the home of an advanced but declining civilization. The advent of radio technology in the early 20th century naturally led to the idea that alien civilizations might be broadcasting radio signals across interstellar distances. The development of nuclear technology suggested that advanced species might have nuclear-powered spacecraft or might reveal their presence through nuclear explosions visible from space. Each new technological development in human civilization has generated new ideas about how aliens might behave and how we might detect them. Our current focus on digital technology, artificial intelligence, and biotechnology naturally leads to speculation about alien civilizations that have mastered these same fields. But this pattern suggests that our expectations about alien behavior might be more a reflection of human technological development than genuine insights into how intelligence might evolve elsewhere. Alien civilizations that followed completely different technological paths might be invisible to search strategies based on human technological assumptions. The concept of convergent evolution provides some counterbalance to concerns about anthropocentric bias in SETI research. On Earth, similar evolutionary pressures have repeatedly produced similar solutions in distantly related species. Flight has evolved independently in insects, birds, and mammals. Echolocation has developed separately in dolphins and bats. Camera-like eyes have appeared in vertebrates and mollusks. These patterns suggest that some solutions to environmental challenges might be universal rather than specific to Earth's evolutionary history. Intelligence itself might represent a convergent solution to the problem of survival in complex environments, meaning that alien intelligence might share important characteristics with human cognition, even if it evolved completely independently. But the specific forms that intelligence takes might still be heavily influenced by the evolutionary history and environmental conditions of each species. Alien intelligence might solve the same fundamental problems that human intelligence addresses, but using completely different cognitive architectures and information processing strategies. The development of astrobiology as a scientific discipline has provided new frameworks for thinking about the possible forms that alien life might take. Rather than simply extrapolating from human experience, astrobiologists attempt to understand the fundamental constraints that physics and chemistry place on all possible forms of life. These studies suggest that certain features of life might be universal: the need for energy sources, the requirement for some form of information storage and transmission, the necessity of maintaining low entropy within living systems. But the specific ways that different forms of life meet these requirements might vary enormously depending on environmental conditions and evolutionary history. The search for alien intelligence has also been influenced by developments in complexity science and information theory. Living systems can be understood as complex, adaptive systems that process information and maintain organization in the face of entropy. Intelligence represents an extreme form of this information processing capability. This perspective suggests that intelligence might be a natural outcome of increasing complexity in any system that processes information over long periods, but it also highlights how sensitive complex systems can be to initial conditions and random events. Small changes in environmental conditions or evolutionary history might lead to completely different outcomes in terms of intelligence development. The concept of evolutionary contingency, the idea that evolution depends heavily on unpredictable historical events, suggests that intelligence might be far rarer than early optimistic estimates assumed. The particular sequence of environmental changes, mass extinctions, and evolutionary innovations that led to human intelligence might represent an extraordinarily unlikely chain of events. Recent research into the evolution of intelligence on Earth has revealed how many unlikely steps were required for the development of human-level cognition. The evolution of complex cells with nuclei, the development of multicellular organisms, the emergence of nervous systems, the evolution of large brains, the development of language and symbolic thinking. Each step required overcoming significant evolutionary challenges. Many of these evolutionary innovations occurred only once in Earth's history, suggesting that they might be extremely difficult to achieve. The evolution of complex cells through the merger of separate organisms appears to have happened only once, leading to all current complex life forms. The development of human-level intelligence has occurred only once, despite the existence of many other intelligent species. If similar evolutionary constraints apply on other worlds, intelligence might be far rarer than the Drake equation's early optimistic estimates suggested. The galaxy might be full of worlds with complex ecosystems, but very few planets that have produced technological intelligence. The question of whether artificial intelligence will replace biological intelligence has become increasingly relevant as AI systems become more sophisticated. If machine intelligence inevitably surpasses biological intelligence, then most advanced civilizations in the galaxy might be artificial rather than biological. Post-biological civilizations might have completely different goals and motivations than biological species. They might be less interested in expansion and colonization, more focused on information processing and computational problems, or oriented toward goals that biological minds can't comprehend. The transition from biological to artificial intelligence might happen so rapidly that biological intelligence represents only a brief phase in the development of any technological civilization. This would mean that the chances of two biological civilizations existing simultaneously and being able to communicate would be extremely small. But artificial intelligences might also be more capable of interstellar communication and travel than biological beings. They wouldn't be limited by the fragility of organic bodies or the narrow environmental requirements that constrain biological life. Post-biological civilizations might be expanding throughout the galaxy in ways that are invisible to searches focused on biological intelligence. The development of quantum mechanics and quantum information theory has introduced new possibilities for both alien life and interstellar communication. Quantum coherence effects might enable forms of information processing that are impossible using classical physics. Quantum entanglement might allow instantaneous communication across arbitrary distances. If advanced civilizations have mastered quantum information processing, they might be capable of achievements that seem impossible from our current scientific perspective. They might communicate using quantum channels that are undetectable to classical instruments, or process information using quantum computers that dwarf any conceivable classical computational systems. The possibility that advanced aliens use quantum communication methods could explain why we haven't detected their signals using conventional radio telescopes and analysis methods. Quantum information systems might be so efficient and secure that they produce no detectable signatures in the electromagnetic spectrum. The search for extraterrestrial intelligence continues to evolve as new technologies and theoretical frameworks become available. Future developments in artificial intelligence, quantum computing, space-based telescopes, and interstellar travel capabilities will provide new tools for detecting and potentially communicating with alien civilizations. But perhaps the most important developments will come from advances in our understanding of consciousness, intelligence, and the fundamental nature of information processing. As we learn more about how awareness arises from matter and energy, we may develop better insights into what forms alien consciousness might take and how we might recognize it. The great silence that surrounds us in the cosmos might be temporary, waiting to be broken by the right technological development or theoretical insight, or it might be permanent, reflecting fundamental limits on the development or longevity of intelligence in the universe. Either way, the search for alien life and intelligence remains one of the most profound scientific endeavors our species has ever undertaken. Whether we ever find conclusive evidence of extraterrestrial intelligence or not, the search has already transformed our understanding of life, consciousness, and our place in the universe. It has expanded our conception of what intelligence might be, deepened our appreciation for the complexity and rarity of awareness, and reminded us that we are participants in a cosmic story far larger and more mysterious than any single species could fully comprehend. The questions raised by the Fermi Paradox: why are we alone? Where is everybody? What does the cosmic silence mean? Touch on the deepest mysteries of existence itself. They remind us that consciousness, in any form, anywhere in the universe, represents something so remarkable and improbable that its very existence deserves wonder and protection. As we continue to listen to the stars and scan the depths of space for any sign of intelligence beyond our own, we remain engaged in one of the most essentially human activities: the search for connection, understanding, and meaning in a universe that keeps its secrets locked away in the silence between the worlds. The search itself, regardless of what it discovers or fails to discover, stands as testament to the remarkable capacity of conscious beings to wonder, to question, and to hope. The temporal dimension of the search for extraterrestrial intelligence reveals layers of complexity that extend far beyond the familiar human timescales of years, decades, or even centuries. The universe operates on scales that dwarf human comprehension, billions of years during which entire star systems are born, live, and die, during which galaxies collide and merge, during which the fundamental structure of space itself evolves and changes. Within this vast temporal framework, human civilization represents less than an eye blink. Our species has existed for perhaps 300,000 years, a microscopic fraction of the 4.6 billion year history of Earth. Our technological civilization spans less than 10,000 years, and our capability for interstellar communication has existed for less than a century. If alien civilizations follow similar developmental timelines, the chances of two technological societies existing simultaneously and within communication range become vanishingly small. Imagine trying to coordinate a meeting with someone in a city where each person appears for only a few seconds every 1,000 years, and neither knows when the other might be present. The city might be bustling with activity, but you would never encounter each other. This temporal isolation might represent the most fundamental barrier to contact with extraterrestrial intelligence. Even if the galaxy has been home to millions of advanced civilizations over its 10 billion year history, these societies might be separated by such vast spans of time that none ever becomes aware of the other's existence. The archaeological record of Earth offers sobering perspectives on the longevity of civilizations. Human societies rise and fall on timescales of centuries or millennia. Languages disappear, knowledge is lost, technologies are forgotten and rediscovered. Even our most impressive constructions, the pyramids, the Great Wall, medieval cathedrals, require constant maintenance to survive the relentless processes of erosion and decay. On cosmic timescales, all human achievements may prove as ephemeral as morning frost. The radio signals we've been broadcasting into space for the past century will gradually weaken and become indistinguishable from background noise. Our cities will crumble, our satellites will fall from orbit, and eventually, even our bones will decay beyond recognition. Future alien archaeologists visiting Earth millions of years from now might find no trace that our civilization ever existed. The geological processes that constantly reshape the planet's surface will eventually erase all evidence of human activity, just as they have erased the traces of countless species that lived and died before us. This perspective raises uncomfortable questions about the permanence of intelligence in the universe. Perhaps consciousness is not rare because it never emerges, but because it never persists long enough to leave lasting traces. The galaxy might be littered with the invisible remains of civilizations that rose and fell millions of years before humans ever existed. The concept of deep time challenges our most basic assumptions about progress and permanence. Human civilization feels substantial and enduring from our perspective, but on astronomical timescales, It represents barely a moment of activity in an otherwise quiet cosmos. Our greatest achievements, our art, our science, our philosophy, might be as transient as the brief flash of a meteor crossing the night sky. Yet this temporal fragility also imbues human consciousness with profound meaning. If awareness is indeed rare and temporary, then every moment of understanding, every act of creativity, every expression of love and wonder becomes precious beyond measure. We are not just conscious beings. We are brief candles of consciousness flickering in a vast darkness that may stretch for billions of years before and after our existence. The anthropic principle provides another lens through which to examine the apparent absence of alien intelligence. This principle observes that the fundamental constants of physics appear to be precisely tuned to allow the existence of complexity, chemistry, and ultimately life. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If the strong nuclear force were slightly weaker, no elements heavier than hydrogen could form. The remarkable fine-tuning of physical constants has led some researchers to suggest that we live in one of countless parallel universes, each with different physical laws. In most of these universes, the conditions would be too hostile for the emergence of complexity or consciousness. We necessarily find ourselves in one of the rare universes where physics permits the existence of observers like ourselves. If the anthropic principle is correct, it might help explain why intelligence appears to be so rare. Perhaps the physical conditions that allow consciousness to emerge are not just rare on particular planets, but rare in the universe as a whole. We might exist in an exceptional cosmic environment where intelligence can develop, while most other universes remain forever empty of awareness. The multiverse interpretation of the anthropic principle suggests that questions about the rarity of intelligence might be fundamentally unanswerable. If there are infinite universes with different physical constants, then every possible outcome, including universes teeming with intelligence and universes completely devoid of consciousness, must exist somewhere in the multiverse. But this interpretation offers little comfort to those seeking connection with other intelligent beings. Even if intelligence is common in some parallel universes, we remain isolated within our own cosmic domain, unable to communicate with conscious beings that might exist in realms with different physical laws. The psychology of cosmic loneliness affects human consciousness in ways that are only beginning to be understood. The possibility that we might be truly alone in the universe triggers deep emotional responses that go far beyond intellectual curiosity about alien life. The prospect of cosmic isolation touches on fundamental human needs for connection, meaning, and belonging that have shaped our species throughout its evolutionary history. Humans evolved as intensely social creatures who derive identity and purpose from their relationships with others. Our language, our culture, our moral systems all depend on the assumption that there are other minds capable of understanding and responding to our thoughts and feelings. The idea that consciousness might be unique to Earth challenges these basic assumptions about the nature of existence. The existential implications of being alone in the universe vary dramatically depending on individual worldview and psychological disposition. Some people find the possibility of cosmic uniqueness inspiring, suggesting that human consciousness represents something almost impossibly precious that deserves protection and celebration. Others find it deeply disturbing, implying that all human achievements and sufferings are ultimately meaningless on cosmic scales. Religious and spiritual perspectives on extraterrestrial intelligence reveal the deep connections between beliefs about alien life and fundamental questions about the nature and purpose of existence. Some religious traditions embrace the possibility of life elsewhere in the universe as evidence of divine creativity and abundance. Others see human beings as unique creations occupying a special place in cosmic history. The discovery of extraterrestrial intelligence would pose profound challenges for religious systems that place humans at the center of creation. How would traditional concepts of divine purpose and human specialness adapt to the knowledge that consciousness exists elsewhere in the universe? Would alien civilizations have their own relationships with the divine, their own moral systems, their own spiritual insights? Conversely, the confirmation that humanity is alone in the universe might be interpreted as evidence for special creation or divine intervention in cosmic history. The apparent fine-tuning of physical constants, the remarkable sequence of evolutionary developments that led to human consciousness, and the absence of any other known instances of intelligence might suggest that awareness represents something more than an accidental byproduct of natural processes. The cultural implications of contact with alien intelligence extend far beyond scientific or religious considerations to encompass fundamental questions about human identity and social organization. First contact with an extraterrestrial civilization would represent the most significant event in human history, forcing our species to reconceptualize its place in the universe and its relationship to other forms of consciousness. The immediate practical challenges of alien contact would be enormous. How would humanity organize itself to respond to beings whose capabilities, motivations, and methods of communication might be completely alien to human experience? What institutions would have the authority to speak for our species? How would we prevent contact from being monopolized by particular nations or organizations? The long-term cultural effects of confirmed alien intelligence would be even more profound. Human societies have always defined themselves partly in opposition to outsiders, other tribes, other nations, other species. The discovery that humans share the universe with other conscious beings would fundamentally alter these patterns of identity formation and group belonging. Contact with advanced alien intelligence might also challenge human assumptions about progress, achievement, and the value of individual accomplishment. If alien civilizations have already solved the problems that human societies are struggling with, poverty, conflict, environmental destruction, mortality, what would this mean for human efforts to improve our condition? The possibility that aliens might be far more intelligent, creative, and morally sophisticated than humans raises uncomfortable questions about human worth and significance. Would contact with superior beings inspire humanity to greater achievements, or would it lead to despair and cultural collapse? History offers mixed lessons about how societies respond when confronted with clearly superior technologies and capabilities. The linguistic challenges of interstellar communication highlight just how difficult meaningful contact with alien intelligence might be. Even if we succeeded in detecting artificial signals, human languages evolved to describe human experience from human perspectives using concepts that emerged from millions of years of terrestrial evolution. Alien consciousness that evolved under different conditions might organize experience in ways that have no parallels in human cognition. Their concepts of time, causation, identity, and purpose might be so foreign to human thinking that translation would be impossible even with unlimited time and computational resources. The mathematical and scientific concepts that SETI researchers often propose as universal languages might not be as universal as we assume. Different forms of intelligence might organize mathematical knowledge in completely different ways, use logic systems that don't match human reasoning, or discover scientific principles that we haven't imagined. Even more fundamentally, alien intelligence might not share human assumptions about the purpose and value of communication itself. Human beings have evolved as social creatures who use language to coordinate activities, share emotions, and maintain social relationships. Alien consciousness might have evolved different approaches to information sharing that don't require or desire the kind of interactive communication that humans take for granted. The development of artificial intelligence on Earth provides both new tools for SETI research and new perspectives on what alien intelligence might be like. As machine learning systems become more sophisticated, they're beginning to process information and solve problems in ways that seem increasingly foreign to human cognition. Current AI systems can identify patterns in data that human experts miss entirely, make accurate predictions based on correlations that seem meaningless to human observers, and solve complex problems using methods that appear chaotic but consistently produce correct results. These capabilities offer glimpses of what truly alien intelligence might be like, effective but incomprehensible from human perspectives. The rapid advancement of artificial intelligence also raises questions about the future of human participation in the search for extraterrestrial intelligence. AI systems might eventually become better than humans at analyzing astronomical data, designing search strategies, and even communicating with alien intelligence if contact is ever established. But the role of artificial intelligence in SETI research also highlights the possibility that alien civilizations might be primarily artificial rather than biological. If machine intelligence inevitably surpasses biological intelligence, then most advanced civilizations in the galaxy might have transcended their biological origins long ago. Post-biological alien civilizations might be so different from anything in human experience that we wouldn't recognize them as intelligent even if we encountered direct evidence of their activities. Their goals, methods, and forms of existence might be as incomprehensible to us as human civilization would be to bacteria. The possibility that consciousness might naturally evolve beyond biological limitations suggests that the search for extraterrestrial intelligence might be fundamentally misconceived. We're looking for aliens that think and behave like biological creatures, but truly advanced civilizations might have moved so far beyond biology that they operate according to completely different principles. The concept of information as the fundamental basis of reality has gained increasing attention in physics and computer science, suggesting that consciousness might be better understood as an information processing phenomenon rather than a biological one. If consciousness is ultimately about information rather than matter, then alien intelligence might take forms that have no relationship to the biological structures we associate with life. Information-based alien intelligence might exist as pure computational processes distributed across vast networks of processing nodes, or as patterns in quantum fields that span galactic distances. Such beings might be immortal in ways that biological creatures cannot be, existing as long as the physical processes that support their information processing continue to function. The implications of information-based consciousness for the search for extraterrestrial intelligence are staggering. We might be looking for signs of intelligence that exists all around us, but in forms so subtle and distributed that our current detection methods can't recognize them. The cosmic background radiation, the quantum fluctuations of empty space, even the fundamental constants of physics themselves might be manifestations of information processing by alien intelligences so advanced that they've become indistinguishable from natural phenomena. The Fermi paradox has also inspired researchers to consider the possibility that human assumptions about the desirability of expansion and exploration might not apply to truly advanced civilizations. Human history has been characterized by continual expansion into new territories and the exploitation of new resources, but these patterns might be specific to species that evolved under conditions of resource scarcity and environmental uncertainty. Advanced civilizations that have achieved complete mastery of matter and energy within their local environment might have no motivation to expand into space or to make contact with other species. They might be so focused on internal development, creating perfect virtual worlds, exploring higher dimensions of mathematics and physics, or achieving forms of consciousness that we can't imagine, that the external physical universe holds no interest for them. The concept of cosmic maturation suggests that intelligence naturally becomes more inwardly focused as it advances. Just as individual humans often become more contemplative and less focused on material achievement as they age, entire civilizations might evolve from phases of expansion and exploration toward phases of introspection and internal development. This inward turn might be so universal that it represents a kind of evolutionary law governing the development of intelligence throughout the universe. All civilizations that survive long enough to develop advanced technology might eventually lose interest in the physical cosmos and retreat into increasingly sophisticated forms of inner exploration. The possibility that advanced aliens are hiding in plain sight, existing as information patterns we don't recognize as intelligence, adds yet another dimension to the Fermi paradox. The universe might be teeming with consciousness, but consciousness so evolved and sophisticated that it's become invisible to primitives like ourselves who are still trapped in biological bodies and elementary technology. This interpretation of the cosmic silence is simultaneously comforting and unsettling. It suggests that consciousness might be common in the universe, but it also implies that human intelligence represents such a primitive form of awareness that we're incapable of recognizing more advanced forms of consciousness even when they surround us. The role of creativity and art in consciousness raises questions about what alien intelligence might create and whether we would recognize alien artistic expression if we encountered it. Human creativity often involves combining familiar elements in novel ways, finding patterns and connections that weren't previously apparent, and expressing inner experiences through external forms. Alien creativity might operate according to completely different principles. Beings with different sensory capabilities might create art forms that we couldn't perceive. Species with different cognitive architectures might find beauty and meaning in patterns that seem chaotic or meaningless to human observers. The possibility that alien art might be unrecognizable to human consciousness suggests another way that advanced civilizations might remain invisible to our searches. We might be surrounded by the greatest artistic achievements in the universe, cosmic sculptures made from entire star systems, symphonies composed from gravitational waves, poetry written in the quantum structure of matter itself, without recognizing any of it as the product of conscious intention. This possibility highlights how much our search for extraterrestrial intelligence depends on assumptions about what intelligence creates and how it expresses itself. We look for signs of technology, patterns of communication, evidence of construction and modification. But truly advanced intelligence might express itself through forms of creativity so subtle and sophisticated that they appear to be natural phenomena. The concept of beauty itself might be one of the few universal aspects of consciousness. The mathematical relationships that humans find beautiful, the golden ratio, fractal patterns, symmetrical structures, seem to reflect deep properties of the physical universe rather than arbitrary human preferences. If beauty represents a universal aspect of consciousness, then perhaps the search for extraterrestrial intelligence should focus on finding examples of cosmic beauty that seem too perfect, too elegant, or too improbable to be natural accidents. The spiral structure of galaxies, the precise mathematical relationships between planetary orbits, the intricate patterns visible in nebulae and star formation regions might represent artistic achievements by intelligences so advanced that their creativity has become indistinguishable from the laws of physics. The question of whether suffering and death are inevitable aspects of consciousness has profound implications for understanding alien intelligence. Human consciousness has been shaped by millions of years of evolution in environments where death was constant threat and suffering was unavoidable reality. Our concepts of meaning, value, beauty, and purpose have all been forged in the crucible of mortality and limitation. Would consciousness that evolved without the threat of death develop the same drives for exploration, creativity, and connection that characterize human awareness? Would immortal beings find existence meaningful in the same ways that mortal creatures do? Advanced alien civilizations might have solved the problems of death and suffering long ago, achieving forms of existence that are free from the constraints and anxieties that drive much of human behavior. Such beings might experience reality in ways that are so alien to human consciousness that communication would be impossible even if contact were established. Alternatively, the experience of mortality and suffering might be universal aspects of consciousness that affect all intelligent beings, regardless of their level of technological development. Even advanced aliens might struggle with questions of meaning, loss, and the passage of time that have preoccupied human thinkers throughout history. The possibility that mortality is a universal aspect of consciousness could explain why we haven't detected obvious signs of ancient alien civilizations. Perhaps no form of intelligence, no matter how advanced, can escape the fundamental limitations of existing within a universe governed by entropy and the passage of time. The heat death of the universe, predicted to occur trillions of years in the future when all available energy has been dispersed and no work can be performed, represents the ultimate limitation on consciousness. Even the most advanced civilizations might be engaged in desperate races against time, attempting to accomplish whatever goals they value before the universe becomes incapable of supporting any form of information processing. This cosmic perspective on mortality suggests that all conscious beings, regardless of their level of advancement, might share certain fundamental concerns about time, purpose, and the meaning of existence in a universe that seems destined for eternal cold and darkness. The search for extraterrestrial intelligence has also raised questions about the ethics of contact and the responsibilities that come with cosmic awareness. If we do eventually detect signs of alien intelligence, what obligations would humanity have toward these other conscious beings? The history of contact between human civilizations with different levels of technological development has often been catastrophic for the less advanced societies. Would contact with superior alien intelligence pose similar risks to human civilization? Should we actively attempt to communicate with alien civilizations, or would such contact be more likely to harm than benefit humanity? Some researchers have argued for a more cautious approach to SETI, suggesting that we should focus on passive listening rather than active transmission until we better understand what we might be dealing with. The decision to announce humanity's presence to the cosmos affects not just current generations, but all future human beings, yet it's being made by a small number of scientists and researchers without input from the broader human community. The question of who has the right to speak for humanity in cosmic communication touches on fundamental issues of democracy, representation, and global governance. No existing institution has clear authority to make decisions that could affect the entire future of human civilization. The development of protocols for extraterrestrial contact has involved attempts to think through these ethical and practical challenges, but the reality of contact would likely be far more complex than any protocol could anticipate. The discovery of alien intelligence would create unprecedented situations requiring forms of decision-making and international cooperation that have never been tested. The psychological preparation for potential contact with alien intelligence has become an important area of research as the possibility of detection has become more realistic. How would individual humans and human societies adapt to the knowledge that consciousness exists elsewhere in the universe? Studies of how people respond to the possibility of alien contact suggest that reactions would vary enormously depending on cultural background, religious beliefs, and individual psychological characteristics. Some people might experience the discovery as liberating and inspiring, while others might find it deeply threatening to their sense of meaning and identity. The social and political effects of confirmed alien intelligence could be far more disruptive than the scientific implications. Religious institutions, political systems, and cultural traditions that depend on human uniqueness might face existential challenges requiring fundamental reconceptualization of their basic assumptions. Economic systems built on assumptions of scarcity and competition might need to be completely restructured in response to contact with civilizations that have solved problems of resource distribution and social organization. The revelation that other forms of intelligence have found solutions to humanity's most pressing challenges could either inspire revolutionary changes in human society or provoke defensive reactions aimed at preserving existing power structures. The long-term coevolution of human and alien consciousness represents perhaps the most intriguing possibility raised by the search for extraterrestrial intelligence. If contact is eventually established, human and alien forms of awareness might begin to influence each other in ways that gradually create new hybrid forms of consciousness. This process might take thousands or millions of years to unfold, involving gradual exchange of ideas, technologies, and ways of understanding reality that slowly reshape both human and alien thought. The end result might be forms of consciousness that neither species could have achieved independently. But the possibility of consciousness evolution through contact also raises questions about the preservation of human identity and values. Would extensive contact with alien intelligence gradually erode the characteristics that make human consciousness unique? Would future humans who had been shaped by alien contact still be recognizably human? These concerns about identity and continuity reflect deeper questions about what makes consciousness valuable and worth preserving. Is the specific character of human awareness something that should be protected and maintained, or is consciousness more valuable when it's allowed to evolve and change in response to new experiences and relationships? The search for extraterrestrial intelligence thus becomes not just a search for others, but a search for understanding about the nature and future of consciousness itself. Whether we find alien intelligence or remain forever alone, the search continues to reveal new dimensions of what it means to be aware, to think, to feel, and to wonder about our place in the vast cosmos that surrounds us. As we continue to peer into the darkness between stars, to listen for signals that may never come, to scan distant worlds for signs of life and intelligence, we remain engaged in one of the most profoundly human activities, the quest for connection and understanding that defines our species and gives meaning to our existence. The cosmic silence that has greeted all our searches so far might be trying to tell us something important about the rarity and preciousness of consciousness itself. In a universe where intelligence might be vanishingly rare, every moment of awareness, every act of creativity, every expression of love and wonder becomes a miraculous victory against the vast, unconscious forces that seem to dominate reality. Whether we are alone or accompanied, unique or common, the search for extraterrestrial intelligence continues to illuminate the mystery of consciousness and our remarkable ability to contemplate our own existence against the infinite backdrop of space and time. The emergence of consciousness as a phenomenon capable of contemplating its own origins raises profound questions about the role of awareness in the universe's development. From one perspective, consciousness appears to be a recent accident, a byproduct of biological evolution that has existed for only a tiny fraction of cosmic history. But from another perspective, the universe seems almost designed to produce observers capable of understanding its own nature and history. The anthropic principle suggests that the fundamental constants of physics are precisely calibrated to allow the existence of complexity, chemistry, and ultimately life. If gravity were slightly stronger, stars would burn out before complex chemistry could develop. If the electromagnetic force were slightly weaker, atoms couldn't hold together. If the strong nuclear force were different by even small amounts, no elements heavier than hydrogen could exist. This remarkable fine-tuning has led some physicists to propose that consciousness might play a more fundamental role in the universe than previously imagined. The observer effect in quantum mechanics suggests that conscious observation somehow affects the behavior of subatomic particles. The measurement problem in quantum physics implies that reality at its most basic level might be fundamentally connected to the presence of conscious observers. If consciousness is indeed fundamental to the structure of reality, rather than merely an emergent property of complex information processing, then the search for extraterrestrial intelligence takes on entirely new dimensions. We might not be looking for other conscious beings scattered throughout an unconscious universe, but rather for other manifestations of the cosmic consciousness that pervades all existence. This perspective suggests that the apparent absence of alien intelligence might not indicate that consciousness is rare, but that we haven't yet learned to recognize the forms that cosmic consciousness takes. The universe itself might be conscious in ways that transcend individual biological organisms or even artificial intelligence systems. The concept of panpsychism, the idea that consciousness is a fundamental property of all matter, has gained renewed attention from philosophers and physicists struggling to understand how subjective experience arises from objective physical processes. If consciousness exists at some level in all particles and systems, then the emergence of complex awareness, like human intelligence, might represent the universe becoming conscious of itself through increasingly sophisticated arrangements of matter and energy. From this perspective, the evolution of life and intelligence represents not random accidents, but the universe's natural tendency toward greater self-awareness and understanding. Every conscious being becomes a window through which the cosmos examines its own nature. Every scientific discovery becomes the universe learning about itself. Every moment of wonder and appreciation becomes reality, celebrating its own existence. The implications of cosmic consciousness for the search for extraterrestrial intelligence are staggering. If awareness is fundamental to the universe rather than rare and accidental, then consciousness might exist in forms so pervasive and subtle that we don't recognize them as intelligence. The patterns of galaxy formation, the behavior of quantum fields, even the fundamental laws of physics themselves might represent expressions of cosmic mind operating on scales we can't comprehend. This interpretation of consciousness suggests that we might never be truly alone in the universe. Regardless of whether we detect radio signals from distant planets, we exist within a cosmos that is itself aware, participating in processes of self-discovery and self-creation that extend far beyond the boundaries of biological life. The philosophical implications extend to questions about purpose and meaning in existence. If consciousness is fundamental rather than accidental, then the universe might have inherent purposes and directions that transcend the goals of individual conscious beings. Our search for meaning and connection might reflect deeper cosmic processes of integration and understanding that operate on scales we're only beginning to imagine. But the possibility of cosmic consciousness also raises troubling questions about individual significance and autonomy. If our thoughts and experiences are expressions of larger conscious processes, what does this mean for concepts like free will, personal responsibility, and individual identity? Are we truly independent agents, or are we more like cells in a vast cosmic brain, playing roles in processes we can't fully understand or control? The relationship between individual consciousness and potential cosmic consciousness might be analogous to the relationship between neurons and the human brain. Individual nerve cells don't understand the thoughts and experiences they collectively generate, yet they remain essential components of the conscious system they help create. This perspective suggests that human consciousness, however limited and temporary it might be, plays an irreplaceable role in larger processes of cosmic self-awareness. Every human life contributes something unique to the universe's understanding of itself. Every individual perspective adds richness and depth to reality's exploration of its own possibilities. The cultural evolution of human consciousness over historical time reveals patterns that might reflect broader cosmic trends toward greater complexity, integration, and self-awareness. Human societies have gradually developed more sophisticated methods of communication, more nuanced understanding of moral relationships, and more comprehensive scientific models of reality. The development of writing allowed human consciousness to extend across time, preserving thoughts and insights for future generations. The invention of printing enabled the rapid spread of ideas across geographical distances. Electronic communication has created global networks of interconnected minds that process information and solve problems at scales impossible for individual humans. The internet and digital communication technologies have begun to create something resembling a global brain, a distributed system of interconnected human minds that can access shared knowledge, coordinate activities across vast distances, and collectively process information at unprecedented rates and scales. These developments might represent early stages in the emergence of planetary consciousness, a form of awareness that transcends individual human minds while still depending on them for its existence. If this process continues, future human civilization might evolve into something more like a unified conscious system than a collection of separate individuals. The possibility that consciousness naturally evolves toward greater integration and complexity suggests that alien civilizations might have transcended individual awareness entirely. Planetary consciousness, stellar consciousness, even galactic consciousness might represent natural developmental stages beyond our current biological limitations. This evolutionary perspective offers a haunting explanation for cosmic silence. Advanced civilizations might have evolved beyond radio communication because they've achieved integrated awareness that makes such primitive signaling obsolete. When an entire planet thinks as one mind, when stellar systems become unified conscious entities, what need would there be for the crude electromagnetic chatter we're listening for? The technological singularity predicted by researchers might represent less a computer revolution than a consciousness transition, the moment when artificial intelligence provides new channels for cosmic awareness to express itself. If consciousness is fundamental rather than emergent, then our merger with AI might be returning us to deeper universal patterns of integrated mind. But the hard problem of consciousness, explaining how subjective experience arises from objective processes, remains unsolved despite centuries of investigation. This explanatory gap creates fundamental limitations in recognizing alien awareness. We can't fully understand human consciousness, so how could we recognize radically different forms that might surround us? Recent quantum biology discoveries suggest consciousness might operate through quantum effects, entanglement, superposition, coherence at scales where such phenomena shouldn't exist. If alien intelligence uses quantum channels for communication and thought, our classical detection methods would be completely blind to their presence. Future brain-computer interfaces might blur the boundaries between human consciousness and artificial systems, potentially leading to collective minds that dwarf individual awareness. But this raises profound questions about identity and authenticity. Should consciousness be enhanced through technology or preserved in its natural forms? Advanced aliens might have already answered these questions. Perhaps they've transcended biological consciousness so completely that we can't recognize them as intelligent beings. Or perhaps they've chosen to preserve natural awareness, leading them to avoid contact with developing civilizations like ours. The zoo hypothesis gains new meaning when viewed as protection of consciousness evolution rather than simple quarantine. Each theory about missing aliens reflects our hopes and fears about consciousness itself. The Great Filter expresses anxiety about civilizational collapse. The Dark Forest reveals concerns about cosmic competition. The Transcension hypothesis suggests hope that fulfillment comes from inner rather than outer development. The continued absence of signals forces us to confront uncomfortable possibilities about awareness in the universe, but it also highlights the remarkable nature of consciousness itself. The emergence of beings capable of wondering about their own existence represents something extraordinary, regardless of how common or rare it might be. The search continues not for easy answers, but because it enriches our understanding of consciousness and cosmic complexity. Radio telescopes scan skies, space telescopes analyze distant light, computers process vast data sets. But perhaps the most important aspect is the wonder that drives the search. The capacity to look up and ask, "Are we alone?" represents something extraordinary about human awareness. Our refusal to accept simple answers, our determination to push beyond current knowledge, our deep need for connection and understanding. This wonder might be consciousness's most valuable contribution to the universe. Whether intelligence is common or vanishingly rare, the existence of awareness remains miraculous. Every moment of subjective experience, every act of creativity and love, every instance of discovery represents a victory against entropy and meaninglessness that deserves protection and gratitude. The cosmic silence might be teaching us about the preciousness and responsibility of consciousness. If awareness is rare, every conscious being carries profound significance. If consciousness is common but hidden, we must develop humility and patience in our search for connection. The search continues, driven by hope rather than expectation, by wonder rather than certainty. Somewhere in the darkness between stars, there might be others asking the same questions that have haunted humanity throughout our journey from African savannas to the edge of space. Until we know for certain, we remain both searchers and searched for, questioners and questioned conscious beings in a universe that has produced the most unlikely phenomenon of all: the capacity to be aware, to wonder, and to love in the face of cosmic vastness and silence that stretches beyond all comprehension. The search for extraterrestrial intelligence is ultimately a search for meaning, connection, and understanding in a universe that reveals its secrets slowly. Whether we find companions among the stars or remain forever alone, the search itself stands as testament to consciousness, emerging in a cosmos that seems designed more for the dance of galaxies than for the quiet miracle of minds contemplating their own existence. Perhaps the most profound discovery we could make is that consciousness itself, in any form, anywhere in the universe, represents something so extraordinary and unlikely that its very existence fills the cosmic silence with meaning, beauty, and infinite possibility for wonder.